Hello, I would like to welcome you to this session on effective tools for design analysis and multi-objective optimization using the SDI Tools software. The SDI Tools software has been developed to support systems engineering, design for Six Sigma, and product development activities. The tool set includes the Triptych tool and the Apogee tool as the two primary tools within this suite. Additional tools that are available include the Reliability Test Design tool, Distribution Explorer, and the PNC Test Effectiveness Calculator. In the Apogee tool, which is used primarily for analysis and optimization activities, it includes a sensitivity analysis tool, a sensitivity statistical allocation tool, Monte Carlo, and multi-objective optimization tools. So let's look at a specific example of using Apogee and how we may use this as part of a design process where we have a basic design that we can model, but for which this design we have multiple characteristics that need to be satisfied. So in this case, we're going to be designing a cylinder that we'll be manufacturing as a component of a fluid reservoir. And the supplier has identified certain physical dimensions and material properties for this particular design of this cylinder. And we need to do some assessments of the quality of the results. Can we meet the desired specifications if we build it the way that the supplier or that the design team has specified? So the final design, in this case, has the cylinder has a height of 30 centimeters with an assigned tolerance to it. There is an outside diameter of this cylinder with 12 centimeters with an assigned tolerance. The fluid reservoir has a wall thickness of 0.5 centimeters with an assigned tolerance. And the material that we're using to manufacture this cylinder has a particular density in terms of grams per cubic centimeter, with a tolerance also on this particular material density that we're analyzing. So here's the objective. Given that these four parameters define this design, the two parameters we need to satisfy is what is the inside volume of the cylinder that we contain the fluid, and then what is the overall mass of the cylinder also. And we have a specification that has to be satisfied, and these are the specs which were the objectives we're trying to satisfy as part of the particular design that was set up for which these parameters were chosen. So let's do the analysis. Well, we can calculate the volume of the cylinder using simple geometry, and also the mass using geometry, and also the density of the material that we're using here for this particular part. So we can readily calculate what is the volume and what is the mass of this parameter. Now then, our assumptions is that when we manufacture this part, there will be certain process capabilities that kind of go along with the manufacturing uncertainties. Okay, so we've done the capability studies. We know how closely we can manufacture the height, the outside diameter, the wall thickness, how we can control the material density to that operation, those processes. And we're going to assume that each one of these variations that we've basically defined with tolerances is that they're all normal, or at least the height and the outside diameter are normally distributed based on 3 sigma tolerancing. The wall thickness will be uniformly distributed, and the density will follow a triangular distribution. So here we have conditions, some of which are normally distributed and some which are non-normally distributed, and we want to understand the effects of these variations on the achievement of the inside volume and the cylinder mass. So let's go set up a worksheet, and in this case we've formatted a standard Excel worksheet to contain the information that's needed to perform the analysis, and then included some of the other information that we know about this design also. So in this worksheet we've identified the design parameters, the height, the outside diameter, wall thickness, and material density, the nominal values that would be associated with each one of those. Now various responses that we can calculate would be the inside diameter, the inside volume, which is one of the conditions we have a specification on that we've identified, the outside volume of interest. We can then determine the surface material volume, and then from that, along with the density, we can determine the cylinder weight, which we also have a specification that we have to satisfy. Now, from the tolerance information that was provided, we can identify what would be the lower limit and upper limit on each one of our design parameters. And then we can also use this information to determine what would be the standard deviation for these parameters based on the variation information. And then for reference, I just also indicated here what type of a probability density function would be used to represent the variation due to the manufacturing capabilities for each one of these parameters. Okay? So here we have mathematically defined the problem, and we have determined what the nominal is, and the nominal value using these parameters is within the upper and lower spec limits for this response, and the nominal cylinder weight is also within the upper and lower spec limits of the response. But the next question is, if we have uncertainty in each one of the x's, what will be the uncertainty of this response, and what will be the probability that we would be non-compliant with our specifications? In other words, what is the predicted defect rate for this particular design? Well, we could take our worksheet and we will go to the Apogee toolbar, and the first thing we would do is identify click the X button for a particular selected parameter, and a window will come up which will allow us to assign then the type of parameter it is. In this case it's a noise parameter. We can assign the mean value and the standard deviation, and in this case if the values need to be adjusted or we need to edit the distribution, you can click on the Edit Distribution button here, and it will allow you to select from a family of distributions, define the various properties, the variation properties using data or other information you may have available to you. So in this case, we've defined our height and also the outside diameter, which are normally distributed with their distribution properties. We've defined the wall thickness, which is uniformly distributed with its uncertainty characteristics. And then the material density will be defined with its triangular distribution that we specified before. So here, once we've defined a parameter, a particular X parameter, then a blue box or border is placed around that cell to indicate that this parameter has been defined with variation properties using the Apogee tool. So this would be the second step in our analysis process. The third step is go to identify the responses for which you want to perform the analysis. So now then, using once again the Apogee toolbar, we will select a cell, click on the Y button in the toolbar, and we'll be asked to define the name for that particular parameter, what's the lower spec limit, the upper spec limit, and if we have a desired probability of noncompliance, we can specify what that would be. So this probability of noncompliance, if you're looking at Six Sigma, could be 3.4 times 10 to the minus 6 defects. If you're just, or anything else you want to pick, maybe 1 out of 1,000, 1 out of 1,000,000, 1 out of 100, whatever you think is appropriate probability of non-compliance with the specification, you can specify here. So now we have a spreadsheet with defined X's, and as indicated by the red borders, we have defined 2 responses that will subject to our analysis in the subsequent steps. So the first analysis we may perform is, since we do have assigned variation for each one of the parameters, what type of response variation might we expect? Well, this would lead you to doing a sensitivity analysis. And what we're showing on this spreadsheet is the result of performing a sensitivity analysis, which is invoked by clicking the button down here on the toolbar for doing the sensitivity analysis, taking lower level variations and rolling those up, if you will, to determine what the overall response variation is. The result of the sensitivity analysis is a spreadsheet that is another worksheet within your workbook that's added to your existing information. And in this case, what we've identified is that the nominal equation result for weight is 710. We have a spec of lower spec of 625 and upper spec of 775. Now the mean cylinder weight that's determined through the sensitivity analysis is about 710.58, very close to what we have for the equation value. We have determined that the uncertainty in the response, due to the uncertainty of the x's, has a standard deviation of about 58.57. Okay? Now, where did this response standard deviation or variation come from? Well, it's due to the variations that were assigned to each one of the x's that's represented by their standard deviations. And this information was captured in the spreadsheet that we started with. Okay? Part of the sensitivity analysis approach is to determine how the responses change due to changes of the individual parameters. So what we're doing in the tool is computing the first and second order partial derivatives. These are computed in the tool for you. And this information is what's used along with the parameters, standard deviations, and mean values to predict the response mean and the response standard deviations. Now, if we make a normal distribution assumption at this point, and let's say that we do have a normal distribution with a mean of 710.58, a standard deviation of about 58.57, and if we compare that dispersion with our specs of 625 and 775, this would indicate that the area in the tails of this normal distribution outside of the spec limits is going to be a non-complying product. So in this case, we've determined that our probability of non-compliance is about 0.21 approximately, or about 21% of our products will fail due to out-of-spec conditions on this response due to the variation in the individual parameters. And then also the tool will tell you what the contribution of variances are for the individual parameters, so which parameters have the greatest influence on the overall response variation. And then also mean shift contributors that could be due to nonlinearity of the response model as influenced by this variation. So this sensitive analysis worksheet was created for both of our characteristics we're interested in, the inside volume and the cylinder weight, and we're only showing the one for the cylinder weight at this particular time. Now then, if we desired to, since we did have non-normal distributions, we could, with the same setup, go perform a Monte Carlo analysis. We would actually use the distributions for each one of the parameters as part of the analysis rather than making normal distribution assumptions as was applied in the sensitivity analysis tool. So in this case, what we're showing you is both of the results for the inside volume condition and the cylinder weight response and their variations that would be due to the variations of each one of these X parameters. And this is all performed using the same setup that we defined previous to this step. So in this case, what we've identified is that for this given design, one response characteristic, such as cylinder weight, has a probability of noncompliance of about 20-24%, and our inside volume has a probability of noncompliance of approximately 6%. So we have one characteristic which is kind of nominal, okay, a 6% probability of noncompliance, but the cylinder weight is probably purely unsatisfactory within the 20% or so of noncompliance on it. So this is a case where we recognize that we have multiple responses and we need to find to achieve one set of design parameters for the X's that will give us a satisfactory probability of noncompliance for both of these response conditions that we need to satisfy for our stakeholders. So let's see if we could address this through allocation. Okay? Well, the allocation tool is based on, given that you know what the nominal values are for your X parameters, and we can determine what the allowable variation would be of the response to achieve a desired probability of noncompliance. So in this case, we're going to specify that let's try to see if we can get to a desired PNC of 0.01 or 1%. Okay? So on the cylinder weight. Remember, we're starting with the noncompliance of about 24%. Well, we see here that using this allocation technique, and this is a workbook that's created in the tool when you invoke a statistical allocation, is it will allow you to go through and use a technique of assigning standard deviations to individual parameters, and these standard deviations will be computed by the tool in order to achieve the desired probability of noncompliance. So it will give you a set of tolerances that will give you the response PNC you want to achieve, but it doesn't guarantee that it will be a producible design. Okay? So in this case, we see here that we have a set of tolerances we came up with that were determined from the allocated standard deviations, and this could be achievable depending on what your process capabilities are, or the tolerances may be too tight or too loose. So, but this is something that you would evaluate, but the tool will allow you to come up with what the proper allocation would be in order to meet the desired response PNC. So it takes the guesswork out of assigning tolerances. Use your direct method of determining what standard deviations or what tolerances are really desired. Now then, if we have determined a set of tolerances that satisfy maybe our 1% probability of noncompliance for the weight, now then, what's the result of these conditions on the other characteristic of the design, which is the inside volume? In this case, we find out that we did well in one, but now then we're about a 40% probability of noncompliance on the inside volume condition. So we improved one and severely degraded the other. So what we've identified is the need that we need to optimize two responses in our design as a function of a set of common design parameters. Two conditions that we need to satisfy simultaneously. We've tried a couple of approaches, but we can't get there from what we have now. Okay, well this is where multi-objective optimization can come in. And when you're performing a multi-objective optimization, we're going to step back, look at the design, and say, we have assigned particular nominal values to our x's, or we've assigned particular tolerances to our x's, to the design parameters, but why did we pick the particular values that we did? So what we're going to do in the optimization approach is identify a design space for each one of the parameters, and you can also identify design spaces for each one of your tolerances if you desire to do so. You can do either parameters or tolerances, or both parameters and tolerances, depending on what you select. So in this case, we're going to say that for height, rather than picking the value that we had before, that we could pick any value between 25 and 35 centimeters for the height of the cylinder, and we could pick tolerances anywhere between plus or minus 0.03 up to plus or minus 0.1 centimeters for the tolerance on whatever nominal value was selected. And then also we have a range of values that we selected for the outside diameter, a range of values we've selected that was a design space for the wall thickness. But then for our material density, we're going to say that it's basically fixed. Okay, this is a vendor item. The density is going to be 2.7 plus or minus 0.1 grams per cubic centimeter, and that's what we have to live with. So this one has more constraints placed on it. Now then, for the overall design, we want to make sure that the overall outside volume meets a constraint of being less than 5,500 cubic centimeters. We want the material volume to be greater than 250 cubic centimeters. The inside volume P&C, we want to be a 1% probability of noncompliance, and the same way on cylinder weights. We're going to try to achieve a 1% probability of noncompliance for both the inside volume characteristic of this design and the cylinder weight. Now then, furthermore, even though our basic requirement is only have one defect out of 100, we really would like to have a Six Sigma level design, which is possibly 3.4 defects per million against this inside volume characteristic and the cylinder weight characteristic. So we need to find parameters within this design space that will allow us to satisfy certain constraints. These are must achieve, and we have certain design goals that we would like to achieve. And our constraints and goals can be defined using the appropriate functions within the Apogee toolbar for defining each one of those as identified here. So now then, you can go perform the multi-objective optimization, and as a result, I'm showing you the what the original design was and what the final design was, and what we were able to do in order to achieve the result that really would meet our stakeholder requirements, actually meet them very well. So in this design, if you remember, we started with an inside volume and a cylinder weight that had your respective P&Cs of approximately 6% and 24%. Okay? Using the stated values that the engineering team had selected or that the vendor had selected for this design. After going through the multi-objective optimization, the optimization process resulted in a design that had a slightly different height. It's a little bit shorter than what we had before. Slightly different outside diameter. The wall thickness was very close to what we had before also, and obviously using the same material weight. And then we slightly modified our specifications. Not really a big modification from what we had before, but slight modifications in terms of the stated standard deviations to meet each one of these parameters. Then when we go analyze the response for the key requirements, remember you had specifications on the inside volume. We defined a constraint of not to exceed on the inside volume. We had a not less than condition on the surface material volume, and then the cylinder weight we had a requirement. And now then, if we went back and ran the sensitivity analysis and Monte Carlo analysis, using the values selected using the optimization approach, we see that we have a design that is very close to zero defects. We're down now to 21 parts per billion in terms of the predicted PNC for the inside volume, and about 54 parts per billion in the design for the design as far as meeting the cylinder weight requirement. So basically, we've gone from a non-compliant design to a very compliant design using the tools that we've identified, using the optimization tool, and in using it then as kind of the technique to take a defined design approach, but help us determine what the proper characteristics would be to meet certain quality requirements and other technical requirements at the same time. So the Apogee tool set includes functions and features that will allow you to do a variety of analyses using anything that you can represent in an Excel spreadsheet. So it can be as many X's as you want within the limits of your computer that you're using, as many Y responses as you want to deal with. The user interface is very simple. Basically, you define your Excel spreadsheet, either a new worksheet or even one you've done before using Microsoft Excel. And then using the Apogee toolbar, as shown in this diagram in Excel 2007 or 2010, you would use the various functions to define parameters, to define responses, to define constraints, goals, and perform your various analyses such as sensitivity analysis, allocation, Monte Carlo analysis or optimization, and then other tools that will assist you in the editing and definition of your parameters also. Okay. So what we found in using this tool set with a variety of companies and in many different industries is that we find that it's very easy to set up a worksheet and then edit its features to support these type of analysis. So you can start with a new or existing worksheet. You can have any number of X or Y parameters. You define what the X uncertainty is from tolerances, from known distributions that are already specified, or even from data can be used to help you define a distribution or the uncertainty properties on a particular X parameter. The X's can be defined using classical probability density functions. You can use Johnson probability density function methods, or you can use histograms and data sets in the assignment of your X parameter distributions. You can analyze the uncertainty of multiple Y responses. You can perform optimization against multiple constraints and goals, and do the optimization not with just respect to the mean, but taking into account the uncertainty of the response as illustrated or represented by the standard deviation. And then also you can do the optimization against the probability of non-compliance of the response. So you can optimize for quality of the design, which is what we did in our cylinder example that we just discussed. Once you set up a worksheet with defined X's and Y's, you are already set up to do an allocation, a sensitivity analysis, a Monte Carlo analysis, or a multi-objective optimization. And all of the functions are easily accessible and editable from the toolbars that are provided in the Apogee toolset. So in summary, Apogee provides methods for analyzing performance and quality very early in your development process. We can start understanding the impact that parameter uncertainty will have on specification compliance for individual responses. Using these techniques, you can simulate a design, you could simulate a manufacturing process, you could simulate operating conditions within your design, and then you can assess that design against conflicting requirements in order to identify potential solutions that could optimize and overcome the conflicting requirements that you may be dealing with. Using the optimization approach, you're performing a trade study. We talked about looking at various design alternatives when we discussed the triptych tool, And actually, when you run an optimization, you are evaluating thousands of design alternatives in a matter of seconds or minutes, and then using the optimization tool to help you identify what the preferred solution may be and give you a rank order of candidate solutions against a particular model that you've identified. In addition to just helping you define the design and understand the goodness of the results, you're actually performing risk assessment and risk management and starting this very early in your development process. So we found that the Apogee tools really do support a variety of product development tasks, systems engineering, and design for Six Sigma activities. It allows you to analyze all of this information in simple spreadsheets, and then you can share the spreadsheets with others also. So they're just standard Excel worksheets and workbooks once you've completed the analysis using the SDI tools. We found that these techniques really do enhance the productivity for engineers to use established and proven methods as part of their development process. And you can use these techniques to analyze the top-level system response, a characteristic in assembly, a condition over a component, analyze a process, whatever it may be, is the Apogee tools will support these type of activities. So I want to thank you for your attention in this tutorial. If you have any questions, I'll feel free to email me or call me, and I'll address those for you. If you want to give the Apogee tool a try, it's also within the SDI Tools version 3 software, which you can download at stat-design.com. Your initial installation will come with a free 7-day trial for the complete tool set, and then if you're interested, then we can talk to you about extending your trial version or to setting you up with a license, either a limited term license or with a perpetual license. So I hope that you found this information useful. I hope that you're thinking about ways that you could apply these concepts in your design activities, whether it's for parts or processes or systems or whatever. And we look forward to working with you in the future. Thank you very much.